When talking about ideal gas processes, it is important to think through what we actually mean. That frequently we're talking about it in terms of variables or names of processes, but I want to start by thinking about what's actually happening. What does the experiment look like? As you can imagine, that's actually more important than just the terminology. So the experiment looks something like this. We have gas, which is typically in a piston that can move up and down. That piston allows you to change the volume. You can fix the piston in place so that the volume cannot change, or you can imagine, say, grabbing a handle and forcing the piston down. Now, instead of changing the volume by force, you can also change the pressure. That would be allowing the piston to freely go up and down, but instead putting different masses on here. Pressure is force divided by area. The piston has a fixed area. This is, of course, the side view. And if we think about the force then, what's the force downward? Well, just the weight of these blocks and possibly the weight of the piston itself. Frequently we do that rather than visualizing the blocks separately. So the weight of the piston plus the blocks gives us the pressure because the piston must end up in equilibrium. So the force down equals the force up, which relates to the pressure of the gas. Finally, we can control heat transferred in or heat transferred out by putting the container in contact with an energy source, so flame is a constant one, or ice to actually transfer heat out. Another thing we can do is actually put it in contact with like a water reservoir that's at a fixed temperature. So we can control the temperature by putting it in contact with something that has a fixed temperature, or we can put heat in or out using, for instance, flame and ice. Note that we're not going to talk about heat until chapter 19, but I think it's helpful to think about all of these processes right now. So that's experimentally what would be going on. So now let's think about the processes. So there's a bunch of different names, and each one is going to refer to a specific type. Isochoric is constant volume, isobaric is constant pressure, isothermal is constant temperature, adiabatic, which is introduced for the first time in chapter 19, actually refers to a process where no heat enters or leaves, and then you have other processes. You can make the gas undergo a process that is not one of these, that is somehow different. So be aware that you can have a process that is different, but these four processes in a way are special. So what would this look like? We could be changing the masses on the piston. This again would be changing the pressure, which is going to be not an isobaric process, right? So if we change the masses on the piston, we are changing the pressure, so we know it's not isobaric, but then we would have to know something else about it to know what else it might be. We could be constraining, i.e. holding in place the volume, which would be isochoric, or we could be changing the volume in a specific way. We could be adding or removing heat. This can be done through an external temperature, or we could be fixing the temperature, which would be isothermal. Or we could say that our piston is well insulated, that no heat energy can enter or leave. And that would actually be adiabatic because we don't have any heat. So what does and technically I shouldn't have said delta there, just Q. What are the physics quantities that we think about when we do this? Volume, pressure, temperature. So these are our state variables, volume, pressure, temperature, at least three of them. And then heat, which is going to be Q, and work, which you're already familiar with. These two are not state variables. So when we're talking about processes, we might be using any of these to actually describe it, but you should be able to then figure out what's going on in terms of the other two columns. Lastly, we have a new addition to our modeling, and that is quasi-static processes. That whenever we're talking about an ideal gas process, it actually needs to be a quasi-static process. If it is not a quasi-static process, we literally cannot model it with the tools we have. And honestly, I struggle to think about what tools I have with more advanced physics classes to even model this. So quasi-static processes are very, very necessary. The idea is that the process is slow enough that the system remains in thermal equilibrium. So we always assume that the system is starting in thermal equilibrium, and at the end, it's in thermal equilibrium, since the only way you can define the state clearly is to have it in thermal equilibrium. But we're also assuming the process is actually moving so slowly that it is in thermal equilibrium every moment in time. So this is basically saying that PV equals nRT is always true. Now, obviously, it is actually changing. So this is a little hard to think through, but again, we're assuming that it's slow enough. Now, the book gives a counterexample of what would be a case where this is not true. And that would be, for instance, if you have your gas trapped in part of the box and you have a membrane that suddenly bursts. So in this case, you don't have equilibrium, that initially all of your gas is on one side of the box and not on the other. This means that clearly you have a very different pressure here and here. On the other hand, if you imagine a piston moving very slowly, we're only ever interested in the volume to the left of the piston, and we would assume that as long as the piston's moving slowly, that the pressure is the same everywhere. Part of this is the idea that it's reversible. If the piston is moving slowly to the right, it can in contrast, move slowly to the left, and depending on what type of process this is, this could literally be enough to just run the process backwards. On the other hand, in the case where a membrane suddenly bursts, where you have no gas here and all the gas on the left, you don't imagine that there's anything you can do to ever force the gas to be back on the left through thermodynamics alone. So quasi-static processes are part of our simplification that we're always making in order to actually use ideal gas processes.